Hello, everyone. Last time we talked about momentum. We talked about momentum in 1D and 2D, and we talked about if there's no external force, momentum should be conserved. If there is, then the momentum will change, and therefore there's an impulse happening when there's a non-zero net force. So you may figure like from this, from the pattern of the momentum conservation, impulse, you may feel like momentum it has a very similar structure as the energy. So in this video, I'm gonna talk about the difference between momentum and energy, and especially momentum versus kinetic energy, because both of them are physics quantities about moving. So energy conservation and momentum conservation. So the biggest difference between energy and momentum is energy is a scalar, while momentum is a vector. Okay. So when we write energy, we will write energy as E, and when we write momentum, we'll write momentum as this. Okay. So momentum is a vector. And also, another big difference is when we talk about energy, energy can be all kind of different form, where spring potential energy, gravitational potential energy, kinetic energy, heat energy, PE, spring, heat energy, we can have nuclear energy. There's a lot of energies. And all this energy will be conserved as long as your system is isolated. But we never talk about potential momentum or heat momentum. Momentum is just momentum. Momentum is mv. So momentum cannot be converted into any other forms. It has just one form, which is mv. Okay. So in some sense, momentum is more like kinetic energy, but they are also somewhat different. Okay. So in momentum, momentum is the only form which is always conserved in an isolated system. Kinetic energy is also a physics quantities that can be transferred between different objects. But kinetic energy is a scalar. But kinetic energy is never conserved because it can be converted into other different energy form, even in an isolated system. So if we make a table to compare them side by side, you can see kinetic energy is 1/2 mv squared. Momentum is mv, and with direction. One is scalar, one is vector. If there's any external force, then that external force will cause if there's any external force acting on the system, then we can use the work energy theorem, because the work done by this net external force will cause the change in momentum. Okay. And work is Fd cosine theta. Similarly, if there's any external force, then that external force will cause the change in momentum. So you see, external force will cause the change in kinetic energy. It will also cause the change in momentum. But the way that cause the change is slightly different, because one is through Fd cosine theta, one is just F delta T. Okay, so one is related to how long, like in distance, that you push this this object, while another one is like how much time you push this guy. So it's very similar but slightly different. If there's no external forces, momentum will be conserved. But you never hear about kinetic energy conserved, because it's not. Even though there's no external forces, kinetic energy can still be converted into other different type of energy. So the biggest difference here, you can see the side by side, so you can see there's a lot of difference between kinetic energy and momentum. Okay, so let me give you an example about the last part. What do we mean by kinetic energy is not conserved, but momentum is always conserved in an isolated system? So remember the bump example that we talked about? So you see this is a bomb, and in this bomb there's some chemical energy, and then which will cause explosion. So when this explosion happens, remember we talked about all the little pieces on this bomb, it will be explode and scattered into all directions. And it has to be in all directions so that the vectors, when you add up all these directions, they will be add up to be 0. So momentum is conserved in this case. You know, initial should be 0. The final, when you add them up, considering all the directions, it should be 0 as well. But is kinetic energy conserved in this case? Let's see. Initially, this guy is not moving. So the kinetic energy of the bomb is 0. The kinetic energy of the bomb event after explosion is definitely not 0 because every little pieces has its own mass and its own speed. And because its speed is square, so your kinetic energy for each little pieces, they are all positive number. These are all positive number. When you add up all this positive number, you will get a huge positive kinetic energy. So you see, in this case, kinetic energy initial is not kinetic energy final, but momentum is. Because momentum has this direction. Direction will make all the MV canceled out. So the conclusion here is, even though kinetic energy is not conserved, but energy is still conserved. Because initial energy, because it is initial the chemical energy that converted into the final kinetic energy. So here, even though kinetic energy, no, it's not conserved, but energy is, because we have a chemical energy. Initially, we still have chemical energy, and then we'll convert it into kinetic energy. So that's the biggest difference. And then later on, we will talk about like some collisions where sometimes momentum is conserved, sometimes energy is conserved, sometimes both of them are conserved, sometimes both of them are not conserved. So, all right, now let's take a look at this example. There's a spring, and when you push the block into the spring will keep it compressed, and when you let go, the box is gonna slide to the right. So how would you compare their kinetic energy and momentum? So if we just look at the block itself, you can see the block initially it's not moving and then it's moving. So apparently you can see there is a spring force pushing it to the right. So the energy is not conserved and neither momentum. But if we look at this whole thing as a system, then we can see that there's no external force, so which means that it's a spring energy converted into the kinetic energy. So if we look at the system, energy is conserved. So let's go from there. Since the energy is conserved, so we know that for A initial energy equals to final energy. Initial is spring energy, spring potential energy. Final is kinetic energy. And for B, it's the same. I'm gonna write it here. So for B, it's the same. So initially we have the same spring energy, and final it's turned into the kinetic energy. Well, I'm gonna make this K bigger. Okay. So if we compare the kinetic energy of both systems, they should be the same because they get the same energy from the spring. So our first conclusion is the kinetic energy will be the same. So now we know that the kinetic energy are the same in both cases. If they are the same, then next we wanna compare the momentum. We don't want to compare Well, when we compare, I mean, the total momentum of the system, because there's no net force, the total momentum should be 0. But it's hard to analyze the momentum of a spring because it's lengthy and the momentum of each hoop will be different. So it's too tedious. I'm gonna start from what we know about kinetic energy, go from there and start from there to momentum. Since the kinetic energy are the same, so we know 1/2 mv squared. This is a constant, it's a fixed number. Right? Because 1/2 mv squared in A equals 1/2 mv squared in B. So that's also telling me that my mass, the mass here, the mass of the object is proportional to inverse of V squared. Or we can say V squared is proportional to the inverse of mass, inversely proportional to the mass. And therefore, we can say the speed or the velocity is inversely proportional to the square root of mass. So from here to here, I just do the square root on both sides. All right, now let's compare the momentum. The momentum is mv, right? But the speed, because kinetic energy is the same in both cases, so the velocity of the object is inversely proportional to 1 over square root of m. Okay. So proportional to. So m divided by root of m, square root of m, it will be this. So it means the momentum of the object is proportional to the square root of mass. If the mass is heavier, then the momentum will be greater. So that means B has a greater mass. That means momentum of B will be greater as well. So PB is greater than, PB is greater than PA. So you can see this is also, this is a more like advanced analysis with the proportionality. So basically from energy conservation, I find this fact and I use the proportionality to help me find what's happening in momentum.